There's a glacier in Antarctica the size of Florida. Right now, as you're watching this, it's cracking apart. Warm seawater is carving cavities beneath it, melting it from below at a rate scientists can barely measure fast enough. If Thwaites Glacier collapses completely, global sea levels will rise by more than 2 feet. Miami, New York, Shanghai, entire island nations, redrawn. But Thwaites isn't just ice. It's a cork holding back the West Antarctic Ice Sheet. Lose the cork and you lose another 10 feet of sea level rise. Scientists have known this for decades. What they believed was that they had time, perhaps 50 or 100 years, before a critical threshold was crossed. In March 2024, new data came back from beneath the ice. The threshold had already been crossed, not in the future, but years ago. And the process now underway can't be stopped. But to understand what that threshold means, you have to go back to the beginning, to a place no human had ever seen. The discovery, February 1947. 13 ships, 23 aircraft, 4,700 men. Operation Highjump was the largest Antarctic expedition ever mounted. For 8 months, Navy pilots flew grid patterns over the continent, photographing coastlines that existed only as blank spaces on maps. A geologist aboard one of those flights spotted something through the clouds, a massive river of ice, 120 kilometres wide, draining into the Amundsen Sea. It moved so much ice that it carved channels through the floating ice shelf in front of it. They named it after Frederick Thwaites, a glaciologist from the University of Wisconsin who studied ice sheets, but would never set foot on this one. The photos showed a glacier larger than any in the Northern Hemisphere. But photos couldn't show what mattered, how fast it was moving, what lay beneath it, whether it was growing or shrinking. The technology didn't exist yet. For 30 years it remained a name on a map, until satellites revealed what was really happening beneath the ice. The first warning, 1973. NASA's. Landsat-1 begins transmitting images from orbit. For the first time, glaciologists can watch ice move in near real time. When they turn the satellite toward Thwaites, the readings don't make sense. The glacier is flowing at more than 4 kilometres per year, which is orders of magnitude faster than stable glaciers in East Antarctica. Then they map the bedrock beneath it using ice-penetrating radar. What they find changes everything. Thwaites doesn't rest on bedrock above sea level like most glaciers. It sits on rock 2,000 metres below the ocean surface. And that bedrock doesn't slope upward toward the sea. It slopes backward, deeper inland. A stable glacier acts like a dam, thickening as it piles up against higher ground near the coast. But Thwaites was built backward. If the ice started retreating, there'd be nothing to stop it. The farther inland it went, the deeper the water got. That backward slope would become the key to everything. But first, scientists had to understand what was holding the glacier in place. The anchor. The glacier itself sits on bedrock, but out beyond its leading edge, the ice keeps going. It floats. This floating extension is called an ice shelf, and it stretches for miles across the water, still hundreds of metres thick, but no longer touching the ground. That shelf is what holds everything back. As the grounded ice behind it tries to slide toward the sea, the shelf pushes against the coastline, against islands, against anything that can resist. The friction slows the flow. Without it, the ice on land would accelerate, pouring into the ocean at 3 or 4 times its current speed. Thwaites' ice shelf covers an area roughly the size of Florida's Everglades, but it's thinning. In some places, it's already fragmented into a maze of rifts and pressure ridges. Scientists call it a buttress, but the better analogy is a cork wedged into the neck of a bottle. Pull the cork, and everything behind it comes loose. The shelf forms where the glacier meets the sea, ice piling onto ice, year after year, compressed under its own weight until it's strong enough to resist the push from behind. For centuries it held, but that anchor was never as stable as it looked. The hidden ocean. Beneath the ice shelf there's an ocean. Not a frozen expanse, but liquid seawater, flowing in slow, persistent currents through a cavity between the ice above and the seafloor hundreds of meters below. The water is cold by any human standard, hovering just above freezing at around 34 degrees Fahrenheit. But that's warm enough. The Amundsen Sea is fed by a deep current system that originates far offshore, where dense, salty water sinks and is replaced by warmer water from the mid-depths. Winds circle the continent, driven by atmospheric pressure patterns that have remained stable for thousands of years. Those winds steer the currents, and the currents carry heat. The warm water doesn't just sit there, it circulates beneath the shelf, melting the ice from below at a rate of several meters per year. You can't see it from the surface. No dramatic carving, no visible cracks. Just the ice thinning, quietly, in the dark. This is the real threat. Not summer air temperatures or surface melt, but the ocean eating away at the foundation. The shelf was always vulnerable from underneath, and for most of history, the water was cold enough that the melting stayed slow. And that ocean was about to grow warmer. The shift. In the 1980s, something changed. A hole opened in the ozone layer above Antarctica, driven by chlorofluorocarbons released decades earlier. The ozone loss cooled the stratosphere, which strengthened the polar vortex and shifted the westerly winds that circled the continent. Those winds, now faster and positioned slightly farther south, began pushing warmer deep water toward the coast. The water temperature beneath Thwaites rose by less than 1 degree Celsius, but that was enough. By the mid-1990s, satellites began detecting changes. The glacier's surface was dropping by 10 centimeters per year in some areas, and its velocity was increasing. Ice that had been moving at 400 ms per year was now moving at 500 ms, then 600 ms. The link was indirect but undeniable. Human-made chemicals had altered the atmosphere, which altered the winds, which altered the currents, which delivered heat to a glacier that had been stable for millennia. The chain of causality stretched across decades and hemispheres, but it was real. Scientists published papers, they issued warnings, but the glacier doesn't respond to warnings. By the time the first alarm was raised, Thwaites had already thinned by more than 100 miles in its fastest moving sections. The ice shelf was weaker. The grounding line had started to retreat. By the time scientists realized what was happening, the glacier had already lost something irreplaceable. The grounding line. The grounding line is where ice meets decision. It's the exact point where a glacier's weight lifts off bedrock and the ice begins to float, transforming from anchored mass into a shelf drifting on seawater. For Thwaites, this line wasn't just geography. It was the hinge holding back 600,000 square kilometres of West Antarctic ice. As long as the grounding line held its position, the glacier stayed locked in place. But when ice thins, the grounding line retreats inland. Each metre of retreat exposes new ice to the ocean beneath, ice that's suddenly vulnerable to water 3 degrees Celsius above freezing. The warmer water melts more ice, which thins the glacier further, which pulls the grounding line back again. It's a feedback loop with no off switch. By 2018, satellites showed the line had moved several kilometres inland since the 1990s. That line had been retreating for decades, but no one knew how fast until a robot ventured beneath the ice. The mission. In October 2018, the International Thwaites Glacier Collaboration began the largest Antarctic field campaign in over 70 years. $50 million, 5 years, 100 scientists from the US and UK, all focused on a single question: how much time is left? They deployed autonomous submarines that could navigate beneath 600 metres of ice shelf, ice-penetrating radar dragged by twin Otter aircraft, and hot water drills designed to bore through ice in conditions where diesel gels at 40 degrees Celsius. Equipment that cost $2 million per unit, routinely vanished into crevasses. The team worked through the Antarctic summer, 24 hours of daylight, then raced to extract data before winter locked the continent in 4 months of darkness. Wind speeds hit 160 kilometres per hour. Tents anchored with ice screws still blew away. One drill rig took 6 weeks just to reach the glacier. But in January 2019, a submarine returned with sonar scans of the ice shelf's underside. The researchers opened the files at McMurdo Station. What they found under the ice rewrote every projection. The cavity. The cavity was 350 metres tall and stretched 40 square kilometres, covering 2/3 the area of Manhattan, carved into the glacier's belly. Sonar revealed its edges, smooth walls of ice rising like cathedral vaults, sculpted by water that shouldn't have been there. NASA's radar confirmed what the submarine saw. That void once held 14 billion tonnes of ice. Most of it had melted in under 3 years, between 2016 and 2019. The melt rate was 6 times faster than models predicted. The cavity sat at the glacier's grounding zone, exactly where ice begins to float. Seawater at 2 degrees Celsius had burrowed beneath the shelf, rising through channels in the bedrock, melting the glacier from within. Every cubic metre of warm water carved deeper, widening the space, pulling more ocean in behind it. It wasn't just melting, it was hollowing. The ice shelf above the cavity was now a 400-metre thick lid floating over open water, still buttressing the glacier but supported by almost nothing. But the cavity was only the symptom. The cause lay further beneath, in a landscape no satellite could see. The bedrock. So they mapped what lay beneath. Ice-penetrating radar sent pulses through 2 kilometres of ice, bouncing off the seafloor below. Sonar from autonomous submarines traced the contours of the bedrock itself, building a picture of the hidden landscape. What they found was a slope tilted the wrong way. Instead of rising inland like a natural barrier, the bedrock dipped backward, descending deeper as it moved away from the coast. The ocean floor dropped from 600 metres below sea level at the grounding line to over 100 metres further inland. Channels carved through the rock like veins, smooth troughs that funneled warm water upstream. There were no ridges, no high points to anchor the ice or block the intrusion. Just a gentle, continuous descent, leading straight into the heart of West Antarctica. It was a topography built for retreat. Once the grounding line began pulling back, each step inland would take it into deeper water, making the ice front taller, more vulnerable, faster to break. That geometry made Thwaites a ticking clock, but no one knew how much time was left. The models. Glaciologists turned to computer simulations. They fed the models everything they knew. The backward slope, ocean temperatures of 1.5 degrees Celsius above freezing, ice velocities measured by satellite, friction coefficients of bedrock and sea ice. Then they ran time forward. The early 2000s projections showed Thwaites destabilising over 200 to 500 years. Slow retreat, gradual thinning, a collapse spread across centuries. The models assumed equilibrium conditions, steady forcing, predictable physics. They were built on the idea that ice sheets change incrementally. Conservative by design, the simulations didn't account for feedback loops that might amplify themselves. They assumed the glacier would respond linearly to warming, that melt rates would stay within observed ranges, that the ice shelf would hold for decades more. These were best-case scenarios dressed as central estimates. But the models only knew what had already happened. They couldn't predict tipping points no one had seen before, couldn't guess at processes the data hadn't yet revealed. Reality doesn't follow models. The acceleration. Between 2000 and 2020, Thwaites began moving faster. Ice velocity at the grounding line went from 2 kilometres per year to over 4. The glacier wasn't just melting, it was sliding, accelerating as the bedrock lubricant of warm water thickened beneath it. The grounding line retreated 14 kilometres inland in 2 decades. Satellite radar tracked it pulling back at 600 metres per year in some places, then 800, then over a kilometre. Every metre of retreat moved the ice into deeper water, lifting more of it off the seafloor, making it lighter, faster, more unstable. Mass loss went from 10 billion tonnes per year in 2000 to 50 billion tonnes by 2020. Cracks appeared on satellite images, fractures spreading across the ice shelf like capillaries, each one a future breaking point. The eastern shelf began fragmenting into icebergs the size of Manhattan. Thwaites wasn't following the 500-year script. It was compressing centuries of collapse into decades, rewriting the timeline in real time. And then, in 2022, scientists saw something that changed everything. The cracks. In December 2022, aircraft fitted with ice-penetrating radar flew grid patterns over the Thwaites ice shelf. The images they captured showed something no model had predicted: a network of fractures cutting across 30 miles of ice, branching like lightning frozen in place. The cracks weren't static. They were propagating at 2 miles per year, faster than the ice itself was flowing forward. Each fracture weakened the shelf's ability to hold back the glacier behind it, turning solid ice into a jigsaw puzzle barely holding together. Engineers call it structural failure. The shelf was still there, still floating, still pressing against the glacier, but its integrity was gone. It was only a matter of time before the pieces stopped holding. But the cracks were only visible from above. Beneath the surface, the ice shelf was already disintegrating. The melt rate. Submarine robots deployed beneath the shelf sent back data that redefined the crisis. Basal melt rates, the speed at which warm water was eating away the underside of the ice, hit 200 feet per year in some zones. Models had predicted 20. The ocean wasn't just warming the ice, it was carving channels into it, hollowing out cavities the size of city blocks, thinning the shelf from below until it was barely thicker than a high-rise is tall. Where the ice was thin enough, surface cracks could punch straight through to the ocean. At 200 feet per year, a 1,000-foot thick section of shelf had 5 years left. In the zones already thinned to 300 feet, the clock read 18 months. The ice shelf wasn't weakening. It was being erased. That melt rate meant the ice shelf had years left, not decades. But scientists still didn't know if it would matter. The domino. Thwaites doesn't sit alone on the coastline. It presses against Pine Island Glacier to the east, and together they form a structural backstop for the glaciers behind them, a 120-mile wide wall holding back a quarter of the West Antarctic Ice Sheet. Remove Thwaites, and Pine Island loses lateral support. Its own ice shelf fractures faster. Its grounding line retreats. The glaciers upstream, no longer buttressed, begin to accelerate. It's not a chain reaction. It's a keystone being pulled from an arch. Satellite data already showed the pattern beginning. Pine Island's flow speed had increased 4% since 2020. Smith Glacier, 40 miles inland, was thinning at its edges. The system was coupled, and Thwaites was the piece under the most stress. That's when scientists began asking a darker question. What if the collapse had already started? The threshold. In glacier dynamics, a threshold isn't a warning. It's a boundary. Cross it, and the system doesn't just change, it transforms into something that feeds itself. For Thwaites, the threshold is geometric. The glacier sits on bedrock that slopes backward, deeper inland. As it retreats, more ice touches warmer water, more melt, faster retreat. The process compounds. Scientists call it marine ice sheet instability. Once retreat begins on a retrograde slope, there's no equilibrium to return to. The glacier doesn't slow down when it loses mass. It accelerates. By 2019, the models all pointed to the same inflection point. If the grounding line pulled back past a series of undersea ridges 20 kilometres inland, the feedback loop would engage. The question wasn't whether that threshold existed, it was whether Thwaites had already crossed it. Finding that threshold required looking not at the ice, but at the ocean. The temperature. In January 2020, sensors lowered through boreholes recorded water temperatures beneath the Thwaites ice shelf, 2 degrees Celsius above freezing. At the seafloor, where the ice was thinnest, the readings hit 2.3 degrees Celsius. That's warm enough to melt 10 metres of ice per year on contact. The source was circumpolar deep water, a mid-depth ocean layer that circles Antarctica, carrying residual heat from lower latitudes. It wasn't supposed to reach the cavity. Antarctic bottom water, dense and cold, normally sits beneath the shelf, insulating the ice. But the warming Southern Ocean had changed the stratification. Circumpolar deep water was intruding onto the continental shelf, slipping beneath the ice through troughs in the seafloor. The sensors showed it pooling directly against the grounding zone. The ice was responding to an ocean that had already shifted into a new regime. Glaciologists had been measuring ice velocity and thickness for decades. The ocean had been changing the whole time, uncounted, but temperature was only half the equation. The other half was time. The proxy. Ice cores from the glacier's surface carry trapped air bubbles, a record of atmospheric composition going back millennia. Sediment cores from the seafloor beneath Thwaites hold forum shells and mineral grains, evidence of when the ice was present and when it wasn't. In 2021, a drilling campaign recovered sediment from 50 metres below the sea floor. The cores showed layers of glacial till, compressed rock and clay deposited by grounded ice. Between them, bands of marine mud, open water. Radiocarbon dating placed the most recent retreat between 12,000 and 9,000 years ago, during the last deglaciation. In that window, Thwaites had pulled back more than 600 kilometres in less than 3,000 years. The retreat hadn't been gradual. It had been rapid, episodic, catastrophic in the geologic sense. The sediment cores revealed something else. Once the retreat began, there was no evidence of re-advance. The glacier had withdrawn to its present position and stayed there. The geologic record contained no story of recovery. And then, in March 2024, the robots brought back data that no one wanted to see. The data. The robots had spent weeks beneath the ice, mapping every contour of the grounding line with sonar and sensors. When the data came back, it showed the line had pulled back 14 kilometres since the last survey. That doesn't sound like much until you look at what it crossed. There's a ridge in the bedrock, a high point where the seafloor rises slightly before dropping away into deeper water. For years, scientists had hoped that ridge would act as a brake, slowing the glacier's retreat. The March survey showed the grounding line had moved past it. Now the glacier sits on bedrock that slopes downward, inland, for hundreds of kilometres. There are no more ridges ahead, no more high points to catch it. The ice is resting on a ramp that tilts the wrong way. That retreat meant the threshold wasn't approaching, it was already behind us. The confirmation. Within weeks, satellite teams began cross-checking the underwater data with their own measurements. Synthetic aperture radar, laser altimetry, GPS stations anchored to the ice. Every instrument pointed to the same grounding line position. They went back through the archive looking for when it happened. The ridge had still been holding in 2017. By 2021, the line had clearly retreated past it. Somewhere in those 4 years, while the models were still predicting decades before we'd reach this point, the glacier had crossed over. Teams around the world fed the new grounding line position into their simulations. They ran the models forward with different ocean temperatures, different melt rates, different ice properties. It didn't matter. Every version showed the same outcome now. But understanding that we'd crossed the threshold was only the beginning. The real question was what happens next. The timeline. The revised models put the ice shelf's complete collapse somewhere between 2029 and 2034. After that, the glacier itself destabilizes within 20 to 60 years, depending on how fast warm water reaches the grounding line and how quickly fractures spread through the ice. There's genuine uncertainty in the speed. Ocean circulation can shift. Ice can fracture faster or slower than the physics suggests. Small changes in water temperature, half a degree, can double or halve the melt rate at the base. But every model, no matter how conservative the assumptions, ends the same way. The shelf breaks, the glacier flows, the grounding line retreats hundreds of kilometres inland before it finds bedrock high enough to stop it. To see what that outcome looks like, you have to imagine the glacier as it is now and watch it disappear. The shelf breaks. The fractures that had been creeping through the ice shelf for years finally intersect. A crack runs 40 kilometres in a week, then splits into branches. The shelf begins to carve in pieces, each one the size of a city block drifting into the Amundsen Sea. What remains thins faster now. The ocean eats at it from below, the air from above. Within 3 years, the shelf that had held for millennia is reduced to scattered icebergs, melting as they drift north. The buttress is gone. The pressure that kept the glacier in place, pressing back against the ice behind it, vanishes in a season. Without the shelf, the glacier's true speed reveals itself. The flow. Ice that had been creeping at 600 metres per year begins to accelerate. Within months, velocity doubles. Within a year, it triples. Satellite radar measures the surface moving at 2.4 kilometres per year, then 3. The glacier's surface drops as ice flows seaward faster than snow can replace it. Crevasses open across the centre line, blue scars against white. Separate ice streams that had flowed in parallel begin to merge, their boundaries blurring as the entire mass surges forward. The physics are simple. Ice is not rigid. It deforms under its own weight. Remove the resistance at the front, and the pressure behind drives everything forward, a slow avalanche measured in kilometres. But the ice isn't just flowing faster, it's thinning, and that thinning pulls the grounding line further inland. The retreat. The grounding line begins to migrate. It retreats 1.2 kilometres the first year, 1.8 the next. Each metre of retreat lifts more ice off the bedrock, exposing the underside to seawater that's 2 degrees Celsius above freezing. The melt rate at the base climbs. More melt means more thinning. More thinning means the grounding line retreats faster, which exposes more ice to the ocean. The loop tightens. By year 5, the line is retreating 3 kilometres annually, following the bedrock as it slopes downward. Models show the process feeding on itself. Each kilometre inland reveals ice that's thicker, under more pressure, resting on bedrock that's deeper below sea level. The forces that had been balanced for 10,000 years are now aligned in one direction. And as the grounding line moves, it uncovers something that makes the collapse unstoppable. The troughs. The bedrock underneath is not flat. It's carved with deep channels, troughs that run perpendicular to the coast, cut by ancient ice flows that shaped this landscape millions of years ago. As the grounding line retreats, warm ocean water doesn't spread evenly across the seafloor. It flows through these channels like rivers, funneling heat directly to the base of the ice in narrow concentrated streams that reach temperatures 2 degrees Celsius above freezing. The deepest trough beneath Thwaites runs 1,200 metres below sea level and extends 120 kilometres inland. It's a highway for warm water, delivering thermal energy exactly where the ice is most vulnerable, where the pressure is highest, where melting destabilises the entire structure. The topography isn't just sloped downward, it's contoured to accelerate the process, each channel a feedback loop that pulls more water inland as the ice thins. That geometry meant the glacier would retreat faster than any model predicted, but there was still a question scientists couldn't answer. The uncertainty. How fast exactly? The models all showed collapse, but the error bars were enormous. A century, maybe 2, possibly 5 if the ocean cooled faster than expected. The physics of fracture are hard to quantify. How quickly does a crack propagate through ice under stress? How does the crystal structure respond to pressure changes? The equations exist, but the parameters depend on measurements taken in conditions no instrument was designed for. Subshelf circulation models require knowing water temperature, salinity, and flow velocity at dozens of points beneath 600 meters of ice. Ice rheology, the way frozen water deforms under its own weight, changes with temperature, with impurities, with strain rate. Climate feedbacks loop back on themselves. Scientists could predict the destination with confidence. The route, the timeline, the exact sequence of events remain blurred by irreducible uncertainty. But even the most optimistic scenarios agreed on one thing: the inevitability. Every credible simulation, even those assuming immediate emissions cuts and rapid ocean cooling, showed Thwaites retreating past its grounding line within this century. The slowest models gave it 200 years, the fastest 50. There is no configuration of future climate where the glacier stabilizes at its current position. The ice shelf will continue fracturing. The grounding line will continue moving inland. The bedrock slope and the deep troughs guarantee it. This isn't a projection of what might happen if we fail to act. It's a description of processes already in motion, momentum already built into the system, heat already absorbed by water that will reach the ice base years from now. Stabilization would require reversing physics that cannot be reversed. 6 research teams, 11 independent models, everyone converging on the same conclusion by 2021. Thwaites Glacier has passed the threshold where intervention is possible, and Thwaites is only the first piece to fall. Pine Island, 150 kilometers to the east, Pine Island Glacier is moving, its ice shelf thinned by 45 meters between 1992 and 2017. Its grounding line retreated 31 kilometers inland. The bedrock beneath Pine Island mirrors Thwaites. The same reverse slope, the same deepening troughs leading inland, the same geometry that makes retreat irreversible once it begins. And as Thwaites collapses, it removes the lateral buttressing that holds Pine Island in place. The ice shelves push against each other, a structural web. When one fails, the neighbouring glacier loses support and accelerates. By 2020, Pine Island's flow velocity increased by 12% in 5 years. The grounding line is retreating faster now than at any point in the satellite record. Together, they hold back something much larger. The ice sheet, the West Antarctic Ice Sheet, spans 2,000 square kilometres. It holds 2.2 million cubic kilometres of ice, enough water to raise global sea levels by 3.3 metres. Thwaites and Pine Island are its outlet glaciers, the drainage valves for the entire sheet. They channel ice from the interior basin toward the Amundsen Sea, controlling the flow rate of the system. Remove those valves and the physics changes. Ice upstream accelerates, thinning spreads inland, the entire drainage basin destabilizes. What takes millennia under stable conditions happens in centuries when the outlets fail. 6 other major glaciers feed into the same embayment, all of them connected by ice shelves, all of them vulnerable to the same cascade, and the ice sheet sits on bedrock that makes it the most unstable landmass on Earth. The basin. The bedrock beneath West Antarctica lies below sea level, in some places 2,500 meters below. The weight of ice has pressed the continent's crust down into the mantle over 34 million years. The center of the ice sheet sits in a deep basin surrounded by subglacial troughs that slope downward toward the interior. These channels run from the coast to the heart of the sheet, pathways for warm water to flow inland once the grounding line retreats. This makes West Antarctica a marine ice sheet, its base in direct contact with the ocean through those submerged bedrock valleys. The same instability mechanism that dooms Thwaites applies to the entire structure. The ice isn't anchored to high ground. It floats on a reverse slope where deeper water lies inland, where every metre of retreat exposes thicker ice to ocean heat. That structure means the ice sheet doesn't just melt, it slides. The cascade. When Thwaites goes, it pulls Pine Island with it. The two glaciers act as gates, holding back the ice behind them. Remove the gates, and the flow accelerates. Interior ice that once crept millimetres per year begins moving metres per day. Grounding lines retreat inland across the basin, one after another. The collapse propagates like a wave through the ice sheet. Glacier by glacier, the entire West Antarctic Ice Sheet begins discharging into the ocean. The mass balance shifts. More ice flows out than snow can replace. The sheet thins from the edges inward. That cascade would take centuries, but once it starts, there's no mechanism to stop it. The timescale. The models place full West Antarctic collapse somewhere between 200 and 1,000 years, depending on how fast the planet warms. This isn't an overnight disaster. It's a slow-motion disintegration playing out over generations. Your grandchildren won't see the end, neither will theirs. But the process, once begun, runs on geologic momentum. Human timescales don't apply. The ice doesn't care about elections or economic cycles. It responds to heat and gravity, and both are working against it now. Centuries sound distant until you realize we're already decades into the process. The grounding line has been retreating since the 1990s. The thinning began before that. But even before the ice sheet collapses completely, the consequences begin. The water. Thwaites alone holds enough ice to raise global sea levels by 65 centimetres, over 2 feet of ocean added to every coastline on Earth. 2 feet redraws maps. It pushes high tides into streets that have never flooded. It turns a 100-year storm surge into an annual event. Miami streets fill with seawater during king tides. Bangkok's canals overflow. Small island nations watch their land shrink. This is just Thwaites, not Pine Island, not the rest of the West Antarctic Basin. One glacier containing enough water to submerge coastal cities and erase coastlines. And that water doesn't rise evenly. The distribution. When ice melts in Antarctica, Earth's gravitational field changes. The massive ice sheet pulls water toward it, like a stone warping a rubber sheet. As that mass disappears, the ocean surface relaxes, dropping near Antarctica, while bulging outward thousands of kilometres away. The physics is brutal in its precision. For every metre of sea level rise from West Antarctic collapse, the Northern Hemisphere gets 1.3 metres. North America, Europe, Asia absorb the excess. The equator sees less. The Southern Hemisphere even less. It's gravity doing the sorting, redistributing trillions of tons of water according to the curvature of space-time itself. Miami rises faster than Cape Town. New York faster than Sydney. Shanghai faster than Johannesburg. Which means the places with the most people face the worst of it. The coasts. Miami sits 2 metres above sea level. Manhattan's financial district 3 metres. Shanghai's waterfront 4 metres. Mumbai, Bangkok, Jakarta, Alexandria, New Orleans. The Mekong Delta feeds 20,000 people. The Ganges Delta, 140,000. The Netherlands holds back the North Sea with 300 to 700 kilometres of dikes. Over 1,000 people live in coastal zones less than 10 metres above current sea level. That's not the count who lose their homes. That's the count who live in the zone before the first storm. Because sea level rise doesn't flood cities by itself. It turns Category 2 hurricanes into Category 5 storm surges. A metre of baseline rise means every high tide reaches what used to be flood stage. Every storm pushes water into subway tunnels, power substations, freshwater aquifers. Every hurricane season becomes a lottery where entire metro areas go offline for months. But the coasts are only the beginning. The collapse changes the entire planet. The circulation. Thwaites melt doesn't just add water, it adds fresh water to the saltiest ocean on Earth. The Southern Ocean surrounding Antarctica drives the thermohaline circulation, the global conveyor belt that moves heat from the equator to the poles and cold water back down into the abyss. That circulation depends on density, salt and temperature. Meltwater is lighter than seawater. It forms a lens on the surface, disrupting the Antarctic circumpolar current, the largest current on the planet. That current connects every ocean basin, cycling 165,000 cubic meters of water per second. When fresh water dilutes the surface layer, dense water stops sinking. The conveyor slows. A slower circulation means heat redistributes differently. Europe cools. The tropics warm faster. Monsoon patterns shift. The feedback tightens. Ice loss freshens the ocean. The ocean changes circulation. Circulation changes climate. Climate accelerates ice loss. One system feeding into the next, each amplifying the last. That disruption was already measurable. The signal. By 2010, ocean sensors anchored to the seafloor in the Amundsen Sea were recording something unexpected. The water was getting fresher. Salinity had dropped 0.03 practical salinity units in 20 years, a shift large enough to register across the entire upper ocean column. The meltwater wasn't staying local. Currents carried it north, a spreading plume of fresh water that began to appear in datasets hundreds of kilometres from the ice front. You could trace it like a bloodstain, diluting as it moved, but unmistakable in its chemistry. Climate models ran the scenario forward. That freshening, if it continued, would begin to interfere with the Atlantic meridional overturning circulation, the conveyor of warm water that keeps northern Europe 5 to 10 degrees Celsius warmer than it would otherwise be. The meltwater, lighter than salt water, would sit on the surface and resist sinking, which means Antarctica's collapse doesn't just raise seas, it cools continents. The paradox. The paradox takes a moment to process. Ice melting from planetary heat can trigger cold. A glacier collapsing in the southern hemisphere can deliver harsher winters to Glasgow, to Oslo, to the coasts of Newfoundland. The mechanism is straightforward. Fresh water from Thwaites disrupts the density gradients that drive ocean circulation. The Gulf Stream weakens. Heat that normally moves north stays in the tropics. Europe, stripped of that subsidy, reverts to the climate its latitude would suggest. Agricultural zones shift. Growing seasons shorten. Storm tracks change course. Not everywhere warms at the same rate, and some places for a time cool. The models showed this decades ago, but now the signal was emerging from the noise. But the collapse also unlocks something scientists are only beginning to measure: the carbon. Beneath the Antarctic ice sheet, buried in sediment and frozen into the ice itself, lies organic matter. Plant material from forests that grew 40 million years ago, microbial mats, carbon that's been locked away since the continent froze. Estimates suggest 21 billion metric tons of organic carbon sits beneath the West Antarctic Ice Sheet alone. As glaciers retreat, that carbon is exposed. Microbes begin breaking it down. Oxygen reaches material that hasn't seen air in geologic time. CO2 and methane start to seep out. Small fluxes at first, but measurable in sediment cores drilled near the ice margin. The loop tightens again. Warming melts ice. Melting exposes carbon. Carbon accelerates warming. Researchers sampled subglacial sediments in 2019 and found microbial activity already underway. Respiration rates higher than expected in such cold, dark conditions. That feedback was still small, but another one was already visible. The albedo. Ice is one of the brightest surfaces on Earth. Fresh snow reflects up to 90% of incoming sunlight straight back into space, never allowing that energy to warm anything. The ocean, by contrast, is dark. Open seawater absorbs more than 94% of the sun's radiation, converting it directly into heat. When an ice shelf the size of Los Angeles disintegrates, it doesn't just remove mass, it replaces a mirror with a sponge. The newly exposed ocean begins absorbing solar energy that would have been reflected away for thousands of years, warming the water column beneath, melting more ice from below. By 2023, the Southern Ocean around West Antarctica had lost enough summer sea ice that the regional albedo had dropped by 0.08 in 2 decades. That translates to roughly 2.3 watts per square metre of additional absorbed energy, the equivalent of leaving a space heater running over every 10 square feet of ocean surface, 24 hours a day, for months. The feedback loop closes on itself. Less ice means more absorption means warmer water means faster melt means less ice. Which is why Antarctica isn't just responding to climate change, it's amplifying it. The amplification. The feedbacks don't operate in isolation. Ice loss warms the ocean, and that warmer ocean melts more ice from below. Ice loss changes the albedo, that darker surface absorbs more sunlight, and regional air temperatures rise by 1.2 degrees Celsius, accelerating surface melt and fracture. Ice loss alters thermohaline circulation, shifting where warm water upwells, redirecting currents toward ice that had been stable for centuries. Each mechanism feeds the others. Warmer water increases basal melt, thinning the ice shelf until it fractures. Fracture exposes new ocean surface, lowering albedo and absorbing more heat. That heat disrupts circulation patterns, pulling additional warm, deep water onto the continental shelf. The system doesn't have a natural break. By 2022, researchers modelling these interactions found that even if atmospheric CO2 was somehow frozen at current levels, the feedbacks already in motion would continue driving ice loss for decades. The ice sheet had crossed from a passive responder, where external forcing alone determined its fate, to an active participant in its own destabilization. Antarctica wasn't melting because the world was warming. It was melting, and therefore the world was warming faster. And all of these feedbacks were accelerating at once. The acceleration. Between 2002 and 2010, Antarctica lost an average of 76 billion metric tons of ice per year. Between 2010 and 2020, that rate climbed to 149 billion metric tons annually. In the 4 years from 2020 to 2024, the rate reached 263 billion metric tons per year. The doubling time had collapsed from a decade to less than 5 years. Satellite altimetry showed the pattern clearly. Ice loss wasn't tracking as a straight line climbing steadily upward. It was a curve, bending steeper with each passing year, the kind of exponential growth that appears gentle at first and then becomes a cliff. The Amundsen Sea sector alone was losing ice 4.7 times faster in 2024 than it had been in 2005. Exponential change is difficult for human cognition to process. We expect tomorrow to look like today, next year to resemble this one. A pond covered in lily pads that double every day looks half empty the day before it's completely full. Our minds are wired for linear extrapolation, for assuming that because the ice took 200 years to retreat 50 kilometres, it will take another 200 to retreat the next 50. But the physics didn't care what felt intuitive. The grounding line was retreating faster each year. The melt rates were climbing. The feedbacks were compounding. But even as the data grew worse, most people never heard about it. The silence. Thwaites wasn't front-page news because it moved like glaciers move, slow, invisible to anyone not watching satellite feeds or drilling through kilometres of ice. A few millimetres of retreat here, a tenth of a degree warmer there. The kind of change you measure in years, not hours. And the science itself carried uncertainty. Models disagreed on timelines. Projections ranged from decades to centuries. That uncertainty became a shield against action, a reason to wait for clearer data. Meanwhile, Funding for Antarctic research competed with 1,000 other crises, and the logistics of studying a glacier the size of Florida in the coldest place on Earth cost tens of millions per season. So the story unfolded in journal articles with titles like Grounding Line Migration and Ice Shelf Buttressing and Basal Melt Rate Variability in the Amundsen Sea Sector. The media covered hurricanes, wildfires, heat waves, things people could see. Thwaites was too far away, too abstract, too slow, until it wasn't. Which raises the question, could anything have stopped this? The intervention. Scientists proposed interventions that sounded like science fiction. Underwater curtains, massive walls anchored to the seafloor, stretching 50 kilometres across the cavity to block the warm water from reaching the ice. Or artificial snow machines pumping seawater onto the surface, freezing it layer by layer to rebuild mass faster than it melted. One team calculated you'd need to remove 100 billion tonnes of water per year from beneath the glacier, pumping it out to reduce the lubrication and slow the slide. The engineering challenges were staggering. The cost ran into trillions. The environmental risks were unknown. What happens when you wall off an entire ocean current? What species depend on that circulation? What feedback loops do you trigger? None of the proposals were feasible with current technology. They required materials that didn't exist, construction on a scale humanity had never attempted, in conditions that destroyed equipment within months. And they all shared one assumption, that you could intervene without making things worse. But even if they were, there was a deeper problem. The commitment. The ocean holds heat for decades. CO2 lingers in the atmosphere for centuries. Even if every power plant shut down tomorrow, even if emissions dropped to zero overnight, the warming already in the system would keep working. Scientists call this climate commitment, the future baked into the present by choices already made. The circumpolar deep water bathing Thwaites' underbelly had warmed by 1 degree Celsius since the 1970s. That heat would keep circulating, keep melting for 50 years or more, regardless of what happened next. The grounding line had already crossed thresholds that made retreat self-sustaining. The ice shelf had already thinned past the point where it could hold back the glaciers behind it. Thwaites wasn't collapsing because of what we'd do in the future. It was collapsing because of what we'd already done. The carbon emitted in the 1980s and 1990s, the heat absorbed by the Southern Ocean through the 2000s and 20s and 10s, the lag between cause and effect, meant the glacier was responding to a climate that no longer existed on the surface, but still lived in the depths. Which means the glacier's fate was sealed years before anyone realized it. The moment. Scientists now believe that moment arrived sometime between 1995 and 2005. Ocean temperatures beneath the ice shelf crossed a threshold, a specific heat content that made grounding line retreat inevitable. The glacier didn't collapse then. It just became certain that it would. By the time the first research teams reached Thwaites in the late 2000s, the process was already locked in. The drilling campaigns, the submarine surveys, the satellite measurements, all of it was documenting a collapse that had been guaranteed years earlier. They were watching an avalanche that had already begun, even if most of the ice was still standing. The lag was the cruelest part. Decisions made in the 1990s determined the fate of coastlines in the 2100s, but the connection remained invisible for decades. A person could live their entire adult life between cause and consequence, never seeing the thread that linked them. But understanding when it was sealed doesn't change what happens next, and that's where the models finally converge. The projection. The Thwaites ice shelf collapses completely by 2030 to 2035. Most simulations agree on that. Without the shelf holding it back, the grounded glacier destabilizes over the following 20 years. By 2100, Thwaites alone contributes 0.5 to 1 metre of sea level rise, maybe more if melt rates accelerate. But Thwaites is the keystone. Its collapse pulls neighbouring glaciers into the same feedback loop: Pine Island, Smith, Pope. The entire West Antarctic ice sheet becomes unstable, adding another 3 metres over the next 200 to 300 years. That's 4 metres total from one section of one continent, enough to redraw every coastline on Earth. These are median estimates, the middle of the range. The worst-case scenarios run faster: ice shelf collapse by the late 2020s, major destabilisation by 2040. Some models show 2 metres by 2100 if warm water intrusion continues to accelerate. The uncertainty isn't whether it happens, it's how quickly the system unravels. That projection is based on everything scientists know, but there was still one thing they didn't understand: the unknown. When a glacier retreats into deeper water, it leaves behind an ice cliff at its terminus, sometimes 80 to 100 metres tall. At a certain height, ice cliffs become mechanically unstable. The weight of the ice exceeds its structural strength, and the cliff face collapses into the ocean in massive calving events, hundreds of metres at a time. This process, marine ice cliff instability, could turn steady retreat into runaway collapse. Instead of the grounding line pulling back a few hundred metres per year, it could jump kilometres in a single event. The ice sheet wouldn't melt, it would shatter, shedding mass faster than any current model predicts. Greenland's Jakobshavn Glacier showed hints of this behaviour in the 2010s, cliffs collapsing in sequences that defied slower melt projections. The physics are uncertain because no one has observed ice cliff failure at Antarctic scale. Lab experiments and smaller glaciers suggest it's possible, but the thresholds aren't confirmed. If it happens at Thwaites, every projection becomes conservative, every timeline compresses, and recent observations suggest it might already be starting. The cliffs. Aerial surveys of Thwaites' calving front reveal cliffs of ice rising 80, 90, sometimes 100 metres above the waterline. They stand where the glacier meets the ocean, sheer faces carved by retreat. Ice this tall creates stress as its own structure can barely support. Lab experiments show that ice cliffs above 90 to 100 metres become unstable. The weight of the ice creates fractures that propagate upward from the base, like cracks spreading through cold glass. When the fractures reach a critical density, the cliff collapses into the sea, exposing fresh ice behind it. This triggers another cycle. A new cliff forms, taller than the last, and the process repeats. The glacier doesn't just melt, it crumbles piece by piece, faster than the ice behind it can stabilise. If those cliffs fail, the glacier's collapse accelerates beyond anything the models predict. But even without that, the outcome is clear. The certainty. The uncertainties don't change the destination. They only obscure the route. Thwaites will collapse. West Antarctica will follow. Sea levels will rise by metres. This isn't speculation or worst-case modelling. It's physics, locked into motion by decades of warming and the geometry of the bedrock below. The grounding line has crossed into deeper water. The ice shelves are fracturing, and the system has no stable equilibrium to return to. The only question left is how fast. Will the collapse unfold over 200 years, giving coastal cities time to adapt? Or will it compress into a century, overwhelming every defence we can build? The models can't say with certainty because we've never watched an ice sheet die before, and when it happens, the world won't look the same. The world. Imagine a planet where sea level has risen 3 metres. Maps are redrawn. Miami, Shanghai, Lagos, entire deltas where hundreds of millions live, gone or walled, behind barriers that cost more than the cities they protect. Some places adapt, others are abandoned. Coastlines erode inward, wetlands drown under salt water, coral reefs sink below the depth where sunlight can sustain them. Permafrost coasts in the Arctic crumble as warmer water eats into cliffs that stood for millennia. Rivers flood backward as their mouths rise with the ocean. Ecosystems built for one climate are forced into another, Migratory birds lose their staging grounds, fish lose their nurseries, and humans lose the infrastructure woven into a shoreline that no longer exists. This is Earth with 3 metres of rise, a world adapted to Holocene sea levels, forced to adapt again. But that future is still centuries away. The collapse we'll see in our lifetimes is smaller, but no less real. The horizon. By 2050, the Thwaites ice shelf is gone. The glacier behind it retreats 5 kilometres inland, its face collapsing into the Amundsen Sea at a pace we've never measured before. Sea level rise, which crept upward at 3 millimetres per year for decades, accelerates to 6, then 8, then 12. Miami Beach goes underwater at high tide, not during storms, during normal lunar cycles. Venice floods 40 times a year instead of 4. The Maldives signs an evacuation treaty with India. 540,000 people preparing to leave islands their ancestors settled 2,500 years ago. This isn't the distant catastrophe of 2300. This is within a single human lifetime, the world your children will inherit before they retire. Coastal cities spend trillions on defences that buy them decades, not centuries. And it's a future that's already locked in. The response. Jakarta is building a 40-kilometre seawall, the largest in the southern hemisphere. The Netherlands floats entire neighbourhoods on pontoons that rise with the tide. New Zealand offers residency visas to Pacific Islanders displaced by water, the first climate refugee program written into law. Humans adapt. We've survived ice ages and droughts, plagues and famines. We're clever, resourceful, capable of extraordinary engineering when survival demands it, but there's a difference between adapting to slow change and adapting to acceleration. You can raise a levee by 2 metres. You can't raise it every decade forever. You can relocate a town. You can't relocate a coastline that holds 600 million people. Adaptation has limits, and those limits are geographic, economic, political. But adaptation to sea level rise doesn't stop the glacier from collapsing, and the glacier is only part of the story. The system. Thwaites is one domino. The Amazon rainforest is another, losing trees faster than it can regrow them, inching toward a tipping point where jungle becomes savanna. Greenland sheds 280 billion tonnes of ice per year, accelerating toward irreversible melt. Siberian permafrost thaws, releasing methane that's been frozen for 40,000 years. These aren't isolated events. They're nodes in a system, and systems have breaking points. When the Amazon dies, it stops absorbing CO2, which warms the planet, which melts Greenland faster. When permafrost releases methane, warming accelerates, which thaws more permafrost. Feedback loops stack on feedback loops. The Atlantic meridional overturning circulation, the current that keeps Europe warm, is slowing by 15% since 1950. If it shuts down, Northern Europe cools by 5 degrees Celsius, while the tropics bake. One tipping point triggers another, and another, until the system we evolved in no longer exists, which is why Thwaites matters beyond the ice. The warning. Thwaites isn't breaking, it's responding. For 200 years, we've been adding carbon to the atmosphere at a rate the planet hasn't seen in 55 million years. And now a system the size of Florida is showing us what happens when you force the Earth that hard, that fast. The glacier is a messenger, not a prediction, not a model. A physical thing you can stand on, touch, measure. A 120-kilometre wide piece of evidence that the rules we thought governed ice sheets were written for a world that no longer exists. It demonstrates something we've struggled to accept, that systems which took millennia to build can unravel in decades, that tipping points aren't theory. They're thresholds you cross, and then the old equilibrium is gone, replaced by something new and irreversible. Thwaites is what instability looks like when it's 192,000 square kilometres and made of ice. But warnings only matter if they're heard. The awareness. In 2024, When the grounding line crossed the ridge, something shifted. News outlets that had never covered glaciology ran the story. Climate summits that had focused on emissions targets started talking about adaptation timelines, about what 3 metres of sea level rise actually means for infrastructure built to last 50 years. Scientists who'd spent careers translating ice core data into careful, hedged projections began speaking differently, not louder, but clearer. The International Thwaites Glacier collaboration published findings without the usual academic cushioning. This is happening. This will continue. These are the consequences. Coastal cities are beginning to incorporate ice sheet collapse into planning, not as worst-case scenarios, but as base assumptions. Singapore's updated its seawall projections. Jakarta's accelerated its relocation timeline. Miami's bond ratings now factor in 2070 inundation maps. The change is slow, incremental, unevenly distributed, but it's real. And the scientists who study Thwaites keep going back. The researchers. Every austral summer, a few dozen researchers return to the ice. Glaciologists, oceanographers, engineers. They fly into McMurdo, take twin otters to field camps, deploy autonomous underwater vehicles beneath the shelf, drill boreholes through 600 metres of ice to measure what's happening where warm water meets bedrock. They're collecting data the world will need for the next century, refining collapse timelines, constraining sea level projections, mapping which parts of the glacier will go first and which might hold on longer. Every measurement narrows the uncertainty. Every season adds another year to the record. But it's not just science, it's witnessing, watching the same ice cliffs every year, noticing the new crevasses, the deeper melt channels, listening to the glacier groan and crack at night, knowing that what you're documenting is something ancient in the process of dying, and you're among the last people who will ever stand on it whole. One researcher described it as studying a slow-motion avalanche while standing in its path. You can't stop it. You can only measure it, understand it, tell everyone downstream what's coming. They go back, because even though the collapse is inevitable, the details still matter. The details. The team measures the speed of the ice, the temperature of the water beneath it, the exact shape of the cavity where warm ocean currents are carving away the base. They drop instruments through boreholes drilled 600 metres down, record the melt rate at different depths, map the bedrock topography that will guide the collapse. Each number sharpens the model. Because when Thwaites goes, it won't be the only glacier to face this. Pine Island Glacier sits next door, grounded below sea level on the same kind of bedrock. Understanding Thwaites means understanding what comes next for the entire West Antarctic Ice Sheet. The data from here calibrates projections for coastlines on every continent. Cities are already building seawalls based on these numbers. Miami, Shanghai, Jakarta, Lagos. The research isn't saving Thwaites, but it might save a neighbourhood, give a coastal town 5 extra years to relocate, help engineers design levees that account for the right rate of rise. The measurements are a map of the future, and in the data, there are moments of unexpected beauty. The ice. The ice itself is older than cities, older than agriculture. Some of it fell as snow 100,000 years ago, compacted under its own weight, layer by layer, into blue ice so dense it barely contains air. When you drill a core from the glacier, you pull up a timeline, volcanic ash from eruptions, dust from ancient droughts, bubbles of atmosphere from when carbon dioxide was 280 parts per million. The researchers sometimes hold pieces of this ice in their hands. It crackles as the trapped air escapes, tiny pockets of the Pleistocene hissing into the present. The water locked inside fell during the last interglacial when sea levels were 6 metres higher and hippos lived in the Thames. Now it's melting back into the ocean, completing a cycle that took 10 millennia. There's something haunting about it. The ice isn't just frozen water, it's frozen time. and as it flows into the Amundsen Sea, it carries with it the climate record of an entire geological age. You can see bands in the ice where centuries of snowfall compressed into single, visible layers. But the glacier is more than ice. It's part of a continent. The continent. Antarctica holds 26.5 million cubic kilometres of ice, 90% of all the ice on Earth. If it all melted, global sea levels would rise 58 metres. Thwaites is a fraction of that, but it's the keystone. The continent is a frozen desert, larger than Europe, colder than Mars in winter, with winds that hit 200 miles per hour and temperatures that drop to negative 128 degrees Fahrenheit. Almost nothing lives in the interior. And yet the ice sheet breathes. It flows toward the sea at speeds measured in metres per year, fed by snow that falls in the highlands and compresses over centuries into glaciers. Thwaites is one of dozens of outlet glaciers draining the West Antarctic Ice Sheet, but it's the fastest, the most unstable, the one that reaches farthest inland. Its collapse won't be an isolated event. It's the continent signalling a threshold crossed. Because Antarctica isn't supposed to change this fast. For millions of years it was stable, locked in equilibrium, gaining as much ice from snowfall as it lost to calving icebergs. That equilibrium is breaking. Thwaites is losing 50 billion tonnes of ice per year now, and the rate is accelerating. The coldest place on Earth is melting. And what's happening there is happening everywhere. The planet. Step back far enough and you see the whole system. The ice in Antarctica isn't separate from the ocean that surrounds it, or the atmosphere that warms it, or the currents that carry heat beneath it. They're all one thing, one continuous loop of water and air and energy moving across the surface of a single planet. The cryosphere, the frozen part of Earth, holds 69% of the world's fresh water. It reflects sunlight back into space, drives ocean circulation, anchors weather patterns. When ice melts, sea level rises. But that's just the most obvious change. Albedo drops, ocean salinity shifts, currents slow, temperature gradients flatten. What happens in Antarctica doesn't stay in Antarctica. A glacier collapses in the Amundsen Sea, and years later rainfall patterns shift in Southeast Asia. Storm tracks bend over the North Atlantic. Coral reefs bleach in the Pacific. The connections are real, measurable, traced by satellites and ocean buoys and atmospheric sensors scattered across the globe. Thwaites isn't just a glacier. It's a node in a planetary network, a pressure point where change in one place cascades into change everywhere else. This is what it means to live on a planet with a climate system. Everything touches everything. The measurement. In November 2023, ESA's Cryosat-2 and NASA's ICSat-2 satellites recorded a grounding line retreat rate of 2.1 kilometres per year at Thwaites' central sector, triple the rate measured in 2017. The glacier's ice velocity increased to 4.7 kilometres per year near the grounding zone, up from 4.2 kilometres per year just 18 months earlier. Ground-penetrating radar from autonomous underwater vehicles confirmed what the models had predicted, but no one had yet seen. The ice shelf's underside was melting in real time at 73 nt per year in some locations, carving cavities large enough to swallow stadiums. Marine ice cliff instability, the runaway feedback loop scientists had warned about for decades, was no longer theoretical. The threshold wasn't a single moment. It was an accumulation of small crossings, each one nudging the system further from stability. But by late 2023, the data converged. The grounding line was retreating faster than the glacier could restabilize. The ice shelf was thinning faster than snowfall could replenish it, and the cliffs were too tall to hold themselves up. Scientists ran the numbers again, cross-checked the satellite passes, verified the radar returns. The answer stayed the same. Thwaites had crossed into irreversible collapse, and the timeline had compressed from centuries to decades. But one glacier, even Thwaites, is not the whole story. The legacy. Thwaites unlocks Pine Island Glacier, which unlocks Smith Glacier, which destabilizes the Getz ice shelf. The collapse propagates inland across West Antarctica like a zipper pulling open, slow but certain. Not this year, not next decade, but across the next 200 to 300 years, 3.4 million square kilometres of ice will respond to the forcing already in the system. By 2300, West Antarctica contributes 3.3 min to global sea level. Miami streets flood at high tide. Shanghai builds seawalls that will be obsolete before they're finished. Bangladesh loses 17% of its land area. The Maldives become a memory. These aren't predictions contingent on future emissions. This is the legacy already written, the consequence of warmth already delivered to the deep ocean. Maps will be redrawn. Coastlines that have been stable for 6,000 years since the Holocene climatic optimum will migrate inland. Cities founded on the assumption of a stable ocean will be abandoned or armoured. Children born today will live to see geography textbooks revised, maritime boundaries renegotiated, entire nations relocate. This is what happens when a planetary system crosses a threshold. The change doesn't stop at the boundary. It propagates, slow and irreversible, across centuries. We set it in motion. We will not see it end. And yet, there is one last thing worth understanding. The witness. In 2023, a glaciologist stood alone on the Thwaites ice shelf at dusk, hydrophone in hand. She lowered the microphone through a drilled hole and recorded something most of us will never hear: the sound of meltwater rivers carving through ice 600 metres thick, a low rumble like distant thunder that never stops. The threshold has been crossed. Warm water now reaches the grounding line year-round. The ice shelf will collapse within decades. The glacier will accelerate, and 3.3 metres of sea level rise is now committed to the system over centuries we won't see. But that recording captured something else. The melt she heard began 11,000 years ago, when the last ice age ended. It slowed for millennia, then accelerated again in our lifetime. The sound is both ancient and new. If this story pulled you in, there are more like it on this channel. Subscribe and we'll keep telling them. Thanks for watching. She stood there for 14 minutes as the light faded, listening. When she finally pulled the hydrophone up, it was covered in frost. She wiped it clean and walked back to camp, the ice creaking under her boots, still solid for now,